Okay, so before I begin, going to download this Llama 3.2, 3 billion parameters. I'm gonna do it instruct instead. Instruct. Uh, instruct. Instruct Q80. Is there a better one? Okay, so quantized 8-bit one, 3.4 gigabytes. Is there one bigger than that? Let's see. Instruct FP16. Let's do that. 6.4 gigabytes, and then let's download it and see how it performs. And we're doing the background while we read through this next chapter here. Whether or not we use it, I don't think it matters. It's just nice to have, especially one that's I hope is going to be more effective than the 1 billion parameter model. All right, so onwards. Threads, chapter 12, and I think this is the last chapter. This is going to be the last chapter of the book. We're going to skip this Blastoids thing, so yeah, it's been a good adventure, and we have way more to do. So don't worry. It's a parallel world. Johnny told me he got his heap variables locked in a mutex. Programs often need to do several things at the same time. POSIX threads can make your code more responsive by spinning off several pieces of code to run in parallel. But be careful, threads are powerful tools, but you don't want them crashing into each other. In this chapter, you'll learn how to put up traffic signs and lane markers that will prevent a code pileup. By the end, you will know how to create POSIX threads and how to use synchronization mechanisms to protect the integrity of sensitive data. Tasks are sequential, or not. Imagine you are writing something complex like a game in C. The code will need to perform several tasks. So, as you run like more complicated games such as applications such as games, they need to do several things at once. And the one thing to remember is that computers with one CPU tend to only do one thing at a time. It looks like things are done in like at the same time because computers are so fast. The operating system is able to switch between each of these programs so quickly that you don't even notice it. Now, when you only have one program running and it needs to do a lot of things, it can actually start to feel slow if you're not using multi-threading. And games are a good example of that because the game needs to do several things. It needs to render graphics, it needs to calculate locations of objects, it needs to play music, and it needs to do like physics and all the other stuff behind the scenes. But you can imagine the game as like a loop, right? It has to do things sequentially. Now, you probably might not notice this, but you're always able to play the game while the music is playing in the background. And actually, that's only possible when you have multi-threading. The game is running in multiple threads. You have one thread for handling audio, you have one thread for updating graphics, you have one thread for handling control input. And what happens is that when you have multiple threads, it allows your operating system to actually treat one of these independently and schedule them and run them separately really fast so that it feels like it's at the same time. If you don't have multi-threading, then really you only have that one piece of code that represents your entire game, where inside will execute that loop of updating graphics, handling control input, and playing music. And so, if that is the case, you can only do one thing at a time. Whereas, you could split that these little things into multiple threads. It's going to feel slow, and this is the reason why you would probably like not hear the music instead, but hear a bunch of random noise. So yeah, so this is what it looks like. These are the things that a typical game might need to do, but it isn't really possible to do it in just one thread. Not only will your code need to do all of these things, it will need to do them all at the same time. That's going to be true for many different programs. Chat programs will need to read text from the network and send data to the network at the same time. Media players will need to stream video to the display as well as watch for input from the user controls. So how can your code perform several different tasks at once? And processes are not always the answer. You've already learned how to make the computer do several things at once with processes. In the last chapter, you built a network server that could deal with several different clients at once. Each time a new user connected, the server created a new process to handle the new session. Does that mean that whenever you want to do several things at once, you should just create a separate process? Well, not really. Here is why. Processes take time to create. Some machines take a little while to create new processes. Not much time, but some. If the extra task you want to perform takes just a few hundredths of a second, creating a process each time won't be very efficient. So what does this mean? It means that the overhead to create a new process just to get a task done that is very short doesn't really warrant the cost, right? It does take time to create a process, and by the time you create one, it's like you spent like maybe $500 just to have something that really only costs like $1, pretty much is what they're trying to say. So sometimes it's not worth creating a new process for a specific task, but at the same time, you really need that task to be done separately. So that's why processes are not really a solution, like creating more of them because of that overhead. Processes can't share data easily. When you create a child process, it automatically has a complete copy of all the data from the parent process. But it's a copy of the data. If the child needs to send data back to the parent, then you need something like a pipe to do that for you. So processes have completely different memory address spaces, so they can't really communicate to each other. So remember, we had to share data between two processes using either like the file system or pipe or some other like message passing mechanisms in order for these two processes or even multiple processes to actually communicate with each other. And processes are just plain difficult. You need to create a chunk of code to generate processes, and that can make your programs long and messy. Yeah, remember the whole fork exec thing? Oh, yeah, that could be difficult. You need something that starts a separate task quickly and can share all of your current data, meaning share the same memory address space and like same variables, same everything. I won't need a huge amount of code to build. You need threads. Simple processes do one thing at a time. Say you have a task list with a set of things you need to do. So here's a shop and serve thing. You run the cash register, stock the shop, re-wax the surfboards, answer the phones, fix the roof, keep the books, or you can just go surfing. You can't do all of the tasks at the same time, not by yourself. If someone comes into the shop, you'll need to stop stocking the shelves. If it looks like rain, you might stop bookkeeping and get on the roof. If you work in the shop alone, you're like a simple process. You do one thing after another, but always one thing at a time. Sure, you can switch between tasks to keep everything going, but what if there's a blocking operation? Meaning, like, what if you need to do something that requires more time, like writing to a file or making a network request? What if you're serving someone at the checkout and the phone rings? You'll probably miss the phone. All of the programs you've written so far have had a single thread of execution. It's like there's only been one person working inside the program's process. So in this case, a thread is kind of like a person and the process is like your business. So processes contain multiple threads. So that's why it's like it doesn't make sense to create another process, like a full-on process, just to complete a task when you can actually create a new thread inside a process to handle that task. So employ extra staff. Use threads. A multi-threaded program is like a shop with several people working in it. If one person is running the checkout, another is filling the shelves, and someone else is waxing the surfboards, then everyone can work without interruptions. If one person answers the phone, it won't stop the other people in the shop. So if you employ more people, more than one thing can be done at once. In the same way that several people can work in the same shop, you can have several threads living inside the same process. All of the threads will have access to the same piece of heap memory. So that's the huge difference here. When you make two processes, they have two different heaps. So you can't really touch each other's heaps. Sounds weird, but yeah. But when you have threads, they can all access the process's heap because they all belong to the same process. That's very useful because then all the stuff that you mallocked before is accessible. They will all be able to read and write to the same files and talk on the same network sockets. If one thread changes a global variable, all of the other threads will see the change immediately. That means you can give each thread a separate task and they'll all be performed at the same time. So how do you create threads? There are a few thread libraries, and you're going to use one of the most popular, the POSIX thread library, or pthread. You can use the pthread library on Cygwin, Linux, and the Mac. Let's say you want to run these two functions in separate threads. Okay, let me respond to something. Yeah, later. I don't know. Okay, so we have two functions. Void does not, which just basically iterates 5 times, sleeps for I guess 1 second. I think this is by seconds, and then outputs does not and returns null when it's done with this iteration. Does two does the same thing. It just outputs does two. Same number of iterations, sleeps for about a second. So returns null again, but I think it's going by here where return a void pointer. So did you notice that both functions return a void pointer? Remember, a void pointer can be used to point to any piece of data in memory, and you'll need to make sure that your thread functions have a void return type. So that's a requirement. Any function that you want to create a thread from needs to return a void pointer, a pointer to a void. So you're going to run each of these functions inside its own thread. So does not, does to. You'll need to run both of these functions in parallel in separate threads. Let's see how to do that. Okay, so we create threads with pthread underscore create. To run these functions, you'll need a little setup code, like some headers and maybe an error function that you can call if there's a problem. Okay, let's start coding. Let's create a new project, and let's do threads demo. Let's create a new file, main.c, and let's get to work. So, include stdio.h, include sdlib.h, include unistd.h, include erno.h, include the special one is going to be pthread.h. And we'll have this function here called error. It'll be a pointer to a character, meaning that's a string. Print f, std error. Print the string, it's an error string here. Message stir error. Okay, and then error no. Okay. Oh, stead error. std error. Okay. Now we will exit 1. So that's our helper to exit the program. Okay, but then you can start the code for your main function. You're going to create 2 threads, and each one needs to have its info stored in a pthread data structure. So this is a data type. Okay, so it contains information about the thread. Then you can create and run a thread with pthread create. So thread 0, thread 1, then create the thread here that will be associated with running does not, and then create the thread here given these threads that will run does to. Okay, should return null, not -1, I guess. No, what does it mean? Oh, pthread create will return either, I guess, some non-negative number. Okay, for success. Okay, the code will run your 2 functions in separate threads, but you've not quite finished yet. If your program just ran this and then finished, the threads would be killed when the program ended. So you need to wait for your threads to finish. If your program just ran this and then finished, the threads would be killed when the program ended. Ah, I see what they mean. So a thread still belongs to the process, right? So when you do this, threads become asynchronous from the main thread, which is basically your process, your program. So your program, when it creates these threads, will just continue to run, and it'll hit like that return 0 in main. So let's just write our main real quick. Okay, so when we create the threads, it'll hit this return 0 and exit. And even though your program needs like 5 seconds, your threads need 5 seconds to execute, your program will totally ignore that because it's doing exactly what it needs to do. Create thread, and then return 0. So we don't want that. We want because if we kill the process, we kill all our threads because threads belong to a process. And so we need a way where if we create these threads, we have to be able to wait for them to finish execution before we kill ourselves so that we can finish all the work. Okay, so before I do that, I'll just update this piece of code here to just show t0, pthread, t1, then we'll go if pthread create t0 null does not null equals -1. We'll say error can't create thread t0, and then we'll have another one pthread create address of t1 null does to null. So if it equals to 1, does 2. Oh, we'll need to write that. We'll need to emit the error. Can't create thread t1. Okay, and now we need to define these 2 functions, does not and does to, which is going to be easy. It's right here. So let's just type that out. Let's do this. Okay, so then we don't need this one here. Then we'll have the same one for does to. Oh, we can just do it like this. Okay, and then we'll have, okay, all this is good. Okay, so that code will run your two functions in separate threads, but you're not quite finished it. The program just ran this and finished. So let's see. Oh, it's still downloading. cd, so threads demo, right? And then we'll do gcc main.c. I'm missing stir error. Am I missing a header? Stir error. I've been missing headers like this. stdio.h, stdlib.h. Oh, maybe string.h. That's why. Okay. Okay, great. Now let's run it. And we exited right away. We probably created those two threads, but we got we killed it right away because of the return 0. Oh, it's a picture of my daughter's Halloween event. It's cute. Okay. So this is how we actually wait for our threads to finish before we proceed. So pthread join. I think it basically kind of subscribes some result to the thread. So we're waiting for the thread to finish, and that will go into our result. So remember that return value of pointer to avoid? I think that's something similar. It has to do with that probably. I'm predicting. So that code will run your two functions in separate threads, but you're not quite finished it, blah, blah, blah. So you need to wait for your threads to finish. So pthread join. The pthread join also receives the return value of your thread functions and stores it in a void pointer variable. Once both threads have finished, your program can exit smoothly. So this is the key, pthread join. So let's do man pthread join. Let's see what that says. The pthread join functions waits for the thread specified by thread by the given thread. I think see right here, thread. The pthread join function waits for the thread specified by the given thread to terminate. Okay, if that thread has already terminated, then pthread join returns immediately. The thread specified by the given thread must be joinable. Okay, if return value is not null, then pthread join copies the exit status of the target thread, i.e. the value that the target thread supplied to pthread exit, into the location pointed by the return value. If the target thread was cancelled, then pthread cancel is placed. This is a constant, this is a number. Pthread is cancel is placed in the location pointed by return value, which is this one right here. If multiple threads simultaneously try to join with the same thread, which is I think the situation here, the results are undefined. If the thread calling pthread join is cancelled, then the target thread will remain joinable. It will not be detached. Okay, so on success, pthread join returns 0. On error, it returns an error number. Okay, cool. So we can just get rid of this. And then we'll just do this. Void result if pthread join t0 result equals -1. We'll have error. Can't join thread t0. And then we'll have another one if pthread join. So after we create a new thread t0, we immediately create t1. It's kind of weird how they share the same result variable. Strange. Can't join thread t1. Oops. Okay, so let's try it. I guess it works. Should I probably just continue reading? I'm guessing it works. Well, it stopped right here. Okay, well, we can probably read on. Because you're using the pthreads library, you'll need to make sure you link it when you compile your program like this. Oh, okay. Maybe gcc main.c link with pthread. Okay. Okay. Maybe. When you run the code, you'll see both functions running at the same time. Hey, it's not. Why? Is it because I'm in tmux? Let's see. Oh, I shouldn't exit that. Tricky. What do I do? I think it's project C. Then I think it was threads demo. Huh, why didn't it work? Did I type something wrong? It's been doing that a lot lately. Pthread join T0 T1. Yeah. What result? I might feel that it's because I'm in tmux, maybe? Huh. Well, let's keep reading and then let's go back and try it out of tmux. So when you run the code, you'll see both functions running at the same time. Okay, so does two, does not, does two, does not. So remember, they're iterating 5 times and then sleeping, meaning like, not doing any activity, and then outputting does not or does two, depending on which thread. So if both functions are running at the same time, why don't the letters in the messages get mixed up? Each message is on its own line. That's because of the way standard output works. The text from put s will all get output at once. I removed the .sleep function and the output showed me all the output from one function and then all the output from the other function. Why is that? Most machines run the code so quickly without the sleep call, so the first function will finish before the second thread starts to run. Makes sense. Okay, so beer magnets. It's time for a really big party. This code runs 20 threads and counts the number of beers going down from 2 million. See if you can spot the missing code, and if you get the answer right, celebrate by cracking open a couple cold ones yourself. Wish. Alright, so basically we're going to create 20 threads. Runs 20 threads. I kind of want to try the other demo first. Well, this is almost done, so we'll exit out of this as soon as possible. Come on. Wow. Wonder how intense my computer is right now. One CPU. It's filling up memory too. Okay, cool. So, sorry, gotta say bye. Okay. I'm going to just exit tmux. Okay, how am I going to do this? Tmux is coming in automatically, so I guess I'm going to do source -rc. Oops, not source, bin -rc. And then I think it's this one we need to comment out because that was like our auto start tmux script. So if I did control, or actually I just do exit and I come back here. Okay, so let's do it. What was I looking at? Oh yeah, cd code. average dev, project, C, threads demo. Oh man, it was not tmux at all. What's going on? Does sleep do something? Seconds, so it's by seconds. Pthread. Oh, we weren't supposed to get rid of this. Oh, that makes sense because we never associated it with code. We never associated with a function. Okay. Yeah, you need both of them. You need to create and then join. Ah, okay. I learned. Okay, so if pthread create t0 null does not. It was nothing to do with tmux. I don't think so. Error can't create thread t0. Okay, another one pthread create, and that makes sense now. Like after you create it, you should wait for it. In hindsight, it does make sense. Does 2 null -1 error can't create thread t1. All right, let's see. Okay, and do we even need to include the pthread library? Let's see. No, we don't. It works. Okay, great. Does 2 does not. Why is that? We're still starting the same. Does 2 does not. Oh, I bet you it's because it's different. Oh yeah. Okay. Does 2. Huh. A different order. Does 2, 1, 2, 3, 4, 5, 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5. Okay, so they have it. Okay. Sleep in I0, 0. So which one's failing? Is it the does 2? Yeah. Ugh. Typo. Sorry. Again. Do this in the afternoon, you're pretty tired by the time you're done with work. So, there we go. We fixed it. Okay, so that works. We got the right result. Alright. So, let's go down here. Now we have another exercise. So I'm going to do threads demo 2. And let's try to solve this ourselves. Let's see here. Threads demo 2. You may not see. By the way, we finished downloading our model, so we can use it anytime we want. I don't know if it matters here, though. Okay, so of course, we're going to have to include all the stuff here. Include sdio.h, include sclib.h, include string.h, include unifcd.h, include erna.h, include the most important one, pthread.h, and then I guess we're going to need this one again. I'm not opposed to just retyping everything. It just helps with practice. Get the reps in, yeah. Okay. Alrighty, so we're gonna have int years. So it's 2 million. 1, 1, 2, 3, 4, 5, 6. Then we'll say void drink. So this is gonna be the function where we're gonna create threads with. So I know that because I see a pointer to a void. And that's my assumption. So drink lots. So it's gonna be a loop for int I equals 0. I is less than, what is this, 100,000? 1, 1, 2, 3, 4, 5. I plus plus beers equals beers minus 1. Return null. And then we're going to have the main. Int main. So let's do this just for practice. Then of course return 0. And we're going to fill this out. Okay, so pthread t is an array of threads, 20 of them. Then we're going to say int t. We're going to do printf. I bottles of beer on the wall, new line. I bottles of beer. Oh, it's like a song. It's the whole bottles of beer on the wall. Beers, beers. And then we're going to have a loop. T equals 0. T is less than 20. T plus plus. Okay, so I'm going to leave that there. I'm pretty sure it's just like, what is it? So all of this is initialized already. So we're just going to do pthread create. And I'm thinking it's going to be threads at t. And it's going to be null. And then here's going to be the function. It's going to be drink lots. And then null. Is it something like this? Let's go back to the pthread create up here. Oh, it's already a function pointer to a function. We drew the name anyway. So back to basics. So we'll create those threads, and then it skips testing for errors, but don't you do that. So I'm going to be good, and I'm going to say if this is equals to -1, I'm going to have an error. Error couldn't create a thread. I'm going to say that. So I'll just create the thread into threads at t, but check the return value of that. If it's -1, then I'm going to throw an error. Okay. Now we're going to do that pthread join thing. But I think that's out of the loop because we're done. This was just to create the thread. Now we're going to have to wait for all of them to finish. So same pattern for t equals 0. T is less than 20, t plus plus. Then we're going to do pthread join. And I think it's just going to be threads, yep, threads t into result. And finally, we have a printf. Printf, there are now I bottles of beer on the wall, new line, beers. Okay. So here's a solution. Pthread create with address. Takes a pointer. We didn't create a pointer. Okay. Then so it takes address of that, null, drink lots, null, and then pthread join. Okay, we did that correctly because I think it was given to us. Okay, so now let's try to run it. So gcc main.c a.out. Okay, there are now 1677173 bottles of beer on the wall. 16 million? 17? What is it? No, 1.6 million and then 1.7 million. Does this actually? So this changes every single time we run it. And this is 2 million, right? Just making sure. 2 million. Okay. 2 million bottles of beer on the wall. 2 million bottles of beer. There are now blah because we were subtracting 100k from each beers on 20 different threads. So technically we should have 0. There are 20. The 20 threads have reduced the beers variable to 0. Hey, wait. Huh? Not 0. Wow. Okay, so I kind of know why. The code usually doesn't reduce the beers variable to 0. That's really odd. The beers variable begins with a value of 2 million. then 20 threads each try to reduce the value by 100,000. So we spawn 20 of these things, 20 threads that will execute the drink lots function. And inside the drink lots function, it will just actually decrement a shared variable up here, which is accessible to all our threads by 1. So technically, if you have 20 threads and you're subtracting this 100,000 times, 20 times 100,000, 20 times 100,000, that should be 2 million, right? Yeah, 2 million. So that should be 0 all the time. What's going on? Huh. Well, the code is not thread safe. The great thing about threads is that lots of different tasks can run at the same time and have access to the same data. The downside is that all those different threads have access to the same data. Unlike the first program, the threads in the second program are all reading and changing a shared piece of memory. So again, the key point here is that these threads are changing a shared piece of memory. The beers variable, changing a shared piece of memory, the beers variable. To understand what's going on, let's see what happens if two threads try to reduce the value of beers using this line of code. So beers equals beers minus 1. Simple. It's just decrementing by 1. So here's what's going on here. First of all, both threads will need to read the current value of the beers variable. So thread 1 and thread 2, they both read 37 at the same time. Then each thread will subtract 1 from the number. So 36, 36. Okay. And finally, each thread stores the value for beers minus 1 back to beers variable. Beers 36, 36. Oh yeah, because they're reading it at the same time, and then they're technically subtracting it and at the same time ish, because they have read it in as that value before, and so it ends up being the same value. So even though both the threads were trying to reduce the value of beers by 1, they didn't succeed. Instead of reducing the value by 2, they only decreased it by 1. That's why the beers variable didn't get reduced to 0. The threads kept getting in the way of each other. So the thing is that whenever the operating system decides to kind of, remember I said that the operating system will switch between different tasks really fast. There's actually no real point where the operating system always switches at. It's unpredictable. It can happen at any time. And the situation is telling us that, okay, we have 20 of these, right? We have 20 threads that run this function, and all of them happen to have read this at some point, all of them in the loop. However, when one thread actually starts reading in and starts subtracting, let's just say right before it subtracts, it knows that beers right now is 2 million. Well, it hasn't subtracted yet, thread 1. The operating system then moves to thread 2 quickly, right? Freezing thread 1 at this point, and it also reads in thread 2 to execute. And then at this point, if let's just say right before it does that subtraction, where it still thinks it's 2 million, it moves on to thread 3, and so on. And then so at some point, all of them are at the same state where they're ready to subtract. And then it so happens that it goes back to thread 1, where thread 1 finally subtracts beers by 1. But keep in mind that at that point, it had read in beers as 2 million. Okay? Now, the operating system says, okay, you're done. Go to thread 2. Now, thread 2 is resuming where it stopped. And at this point, it thought beers was 2 million. And it subtracts 1 from that 2 million. And it does this repeatedly. Sometimes it doesn't even make progress, depending on like your computer. So that's why it feels very random, and that's why it feels like everybody has the same thing. It's just that it so happens it read a value at some point. The operating system goes, okay, your turn is up. Let's go to another task. Let's switch to another task. That task has the same variable value as the previous one, and then these types of things just end up happening. Okay. Oh. Okay, so that's why the beers variable didn't get reduced to 0. The threads kept getting away of each other, and why was the result so unpredictable? Because the threads didn't always run the line of code exactly at the same time. Sometimes the thread didn't the threads didn't crash into each other, and sometimes they did. So this code here is not thread safe. In order to make something thread safe, we have to pretty much protect a variable that's shared by amongst all the threads. So if a thread is operating on a specific variable, another thread cannot just come in and kind of interfere with that. And that's what it means to be thread safe. So you need to add traffic signals. Multi-threaded programs can be powerful, but they can also behave in unpredictable ways unless you put some controls in place. Imagine two cars wanting to pass down the same narrow stretch of road. To prevent an accident, you can add traffic signals. Those traffic signals prevent cars from getting access to a shared resource, the road, at the same time. It's the same thing when you want two or more threads to access a shared data resource. You need to add traffic signals so that no two threads can read the data and write to it back at the same time. So stoplights. You get to go, you don't get to go. You get to go, you don't get to go. Okay? The traffic signals that prevent threads from crashing into each other are called mutexes, and they are one of the simplest ways to make your code thread safe. Mutexes. Sometimes they're just called locks, and I like to use locks more because it's easier to understand. So yeah, so we have a data structure for this. We have a specific data type to represent a mutex. So use a mutex as a traffic signal. To protect a section of code, you will need to create a mutex lock like this. Boom. Okay, pthread mutex t, a lock equals pthread mutex initializer. The mutex needs to be visible to all of the threads that might crash into each other. So that means you'll probably want to create it as a global variable. Pthread mutex initializer is actually a macro. When the compiler sees it, it will insert all of the code your program needs to create the mutex locks properly. So this is actually a bunch of code that gets replaced before you compile this pthread mutex initializer. But not too important for our level. Red means stop. At the beginning of your sensitive code section, you need to place your first traffic signal. The pthread mutex lock will only let one thread get past. All the other threads will have to wait when they get to it. So we just need to do this call right before you start the subtraction, I bet. Yeah, right there. So it's like lock the variable. Green means go. When the thread gets to the end of the sensitive code, it makes a call to pthread mutex unlock. That sends a traffic signal back to green, and another thread is allowed onto the sensitive code. So unlock when you're done. Okay, so that's how you unlock. Now that you know how to create locks in your code, you have a lot of control over exactly how your threads will work. So this is how we do it. We're going to have to... Wait. Okay, so this is going to be what? Do stuff. I'm lost. This seems different from what we were doing. Oh, okay, this is an example. Okay. All right. So thread functions can passing long values to a thread function. Oh, so this is how you would do it if you wanted to pass in parameters or arguments to your thread function, so you can actually access it. Okay, so basically you would just pass it as so this one here as some sort of value. Just pass any value, and then when you want to use it, you need to cast it because this is a pointer to avoid. Oh, right here, pointer to avoid. So you just need to convert it manually. Okay, that's fine. Okay. So there's no simple way to decide where to put the locks in your code. Where you put them will change the way the code performs. Here are two versions of the drink locks function that lock the code in different ways. So here's the one where it locks before the for loop and locks after the for loop. And this is the one where I thought should have been locked at right before the subtraction and then after the subtraction. Which one is correct? So let's see. Both pieces of code use a mutex to protect the beer's variable, and each now displays the value of beers before they exit. But because they are locking the code in different places, they generate different output on the screen. Can you figure out which version produced each of these two runs? I'm guessing this one is A because it subtracts 100,000 at a time, which makes sense because it's locking 100,000 at a time. And I'm guessing this one's code B because it looks like all over the place. But they produce the same result at the end. So but there's no simple okay, fine. Let's see. Why is this? What am I missing? Oh, right here. So this one is A and this one is B. Sure. Okay. Anyway, congratulations. Yay! You've almost reached the end of the book. Now it's time to crack open one of those. Actually, you know what? I'm going to implement it first. I want to implement it. So this Beers lock is going to be globally shared. Here's a lock, and we're going to insert this macro pthread mutex initializer, and then we're just gonna lock. I'm gonna lock it the way I thought it should have been locked. So mutex lock, and then we're gonna pass in the pointer to Beers lock. Okay, and then mutex unlock. We're gonna pass in the pointer there, and then let's compile. Okay, 0. That's great. Fixed it. Okay. All right, now let's go back here. So congratulations, you almost reached the end of the book. Now it's time to crack open one of those 2 million bottles of beer and celebrate. You're now in a great position to decide what kind of C coder you want to be. Do you want to be a Linux hacker or using pure do you want to be a Linux hacker using pure C or a maker writing embedded C in small devices like the Arduino? Maybe you want to go and be a games developer in C++ or a Mac and iOS programmer in Objective-C. Whatever you choose to do, you're now part of the community that uses and loves the language that has created more software than any other. The language behind the internet and almost every operating system. The language that's used to write almost all the other languages. And the language that can write almost for every processor in existence, from watches and phones to planes and satellites. New C Hacker, we salute you. That's amazing, right? We've just learned a language that pretty much works on every single device out there that can actually execute C. It's just amazing. We have the tools now. Does my machine have to have multiple processors to support threads? No, most machines have processors with multiple cores, which means that their CPUs contain many processors that can do several things at once. But even if your code is running on a single core or a single processor, you will still be able to run threads. Yeah, because of the whole switching thing. How? The operating systems will switch rapidly between the threads and make it appear that it is running several things at once. Will threads make my programs faster? Not necessarily. While threads can help you use more of the processors and cores on your machine, you need to be careful about the amount of locking your code needs to do. If your threads are locked too often, your code may run as slowly as a single-threaded code. How can I design my thread code to be fast? Try to reduce the amount of data that the threads need to access. If threads don't access a lot of shared data, they won't need to lock each other so often and will be much more efficient. Are threads faster than separate processes? They usually are, simply because it takes a little more time to create processes than it does to create extra threads. I've heard that mutexes can lead to deadlocks. What are they? So say you have two threads, and they both want to get mutexes A and B. If the first thread already has A and the second thread already has B, then the two threads will be deadlocked because they need each other's resources. This is because the first thread can't get mutex B and the second thread can't get mutex A. They both come to a standstill. All right. That is it. We have finished the book, essentially. Okay. Yeah, where to from here? I need to think about that, but maybe more data structures, maybe a project and data structures here and there. maybe let's try and compile the Linux kernel. I don't know. We'll see. It's been great. Um, yeah, this was straightforward in terms of material. I mean, just reading through the book and doing examples. But I feel like I've gotten better at C. So until next time, thank you, everybody.